Okay, in this video we are going to talk about interference, and so in this picture here we have two speakers and they produce sound with the same frequency and same amplitude, same wavelength of course, but they are located at different positions, right? So the question is what do we hear here? What is the resultant wave here? Well, it's going to depend on this distance, x2 minus x1. And if this distance is such that this maximum and this minimum are in like shown here in the picture, then you're not gonna hear anything here. Okay? If you are able to arrange the speakers, if you are able to change this distance x2 such that the two maximums coincide, then you hear your maximum sound there. So that is interference. That is interference, and let's look a little bit of the math behind it. So we know we can write a wave traveling to the right as the amplitude times the sine of kx minus omega t plus some initial phase. And that initial phase, it tells us what the wave was doing at time equals 0. So for instance here at time equals 0, the wave was 0, so that's a phase of 0 radians. But here it was A, so that's a phase of pi over 2 radians. An initial phase, phase 0, right? So now, constructive interference, that happens when the two waves add up, when you have sound, when you can hear. So for that to happen, then you see that the maximums have to coincide here. So, and that depends on this distance here. So if this distance, as we're going to see later, is such that it is a multiple of a wavelength, then you're going to have a constructive interference. To see that, we can write D1, the wave produced by this speaker, in this way here. And then D2, the wave produced by this speaker, D2 would be written this way. They both have two initial phases here. And the resultant wave, what you hear somewhere here, it would be D1 plus D2. Now, when the two waves are in phase, meaning d1x is equal to d2x, the resultant is the maximum amplitude when the two waves are in phase, like this here, this case here. When they are out of phase, when the two waves are out of phase, like here, this distance here is a multiple of half a wavelength, right? So then they are out of phase. This maximum, the maximums don't coincide. Then you get perfect destructive interference and you don't hear anything. So how do we see that? Well, you can add the two waves mathematically, and you can rewrite these as a sine of phi 1 plus a sine of phi 2. Phi 1 would be this whole thing here. Phi 2 would be this whole thing here. So now we can use a trigonometry identity to write the net displacement, right? So we can rewrite this as an average phase, right? We have an average phase where we have an average position and an average initial phase. And this other factor here, which is 2a, twice the amplitude, cosine of delta phi divided by 2. And this delta phi is the difference between this phase here, this whole thing, this kx1 minus omega t plus phi 1 0, and phi 2, this kx2 minus omega t plus phi 2 0. So that's the difference there. So what is the maximum amplitude that you could have is 2a, and that happens when the cosine is 1, or when the cosine of this thing here, when this cosine here, when this thing is 1, then that's when you get maximum amplitude. That happens when this is equal, the thing inside the cosine equals to a multiple of 2 pi, right? And so that means delta 5, and similarly, you'll get destructive interference when the cosine is 0, or when the cosine is equal to m plus 1/2 times 2 pi. So this is the condition for a maximum constructive interference. This is the condition for perfect destructive interference. So what does this condition means? Well, if the two speakers, right, imagine that they start with the same initial phase, right? They start exactly in the same way when you turn them on, right? So if this delta x is lambda, then you see these maximums are in phase, and that is this condition here, right? And therefore, delta x equals to lambda means maximum constructive interference. So therefore, delta 5 is equal to 2 pi, and you get the maximum amplitude. Now, if delta x is 1/2 lambda, then delta 5 is pi, and then you get the cosine of pi, which is 0, and then you see this is a maximum here, and this is a minimum, and they cancel out. So that's what happens when you have interference in one dimension. So you could have cases in which they are neither out of phase or in phase, and then you're going to have interference, but you're going to have, you're not going to see either maximum constructive interference or maximum or complete destructive interference. You're going to see some sort of in between. Okay. So one application of this is in thin film optical coatings. And what you want there is you want to, if these are your glasses, right, you want to reduce the reflections, right? One way to reduce a reflection is to put a thin film here, and then what happens is there's going to be a wave reflected here, and you can design this thin film, you can design this coating here in such a way that the interference of the two waves, the one coming this way and the other one coming the other way, cancel each other, and that's the principle of anti-reflection coatings. Okay, thank you.